This leaves me with probably the last topic for today, namely a brief discussion of fluctuations. Let's consider again as an example a system that is characterized macroscopically by the expectation value of energy. So again, just like in the harmonic oscillator example, the energy is given as an expectation value, and hence we work with a canonical state. This is now not limited to the harmonic oscillator. This is a general consideration. So we take an arbitrary system macroscopically characterized by the expectation value of energy, and hence its macro state has the form of a canonical state. We know that when we take the partial derivative of the log of the partition function, this is the same as 1 over partition function partial of z with respect to beta. But we know from our general considerations that this is equal to minus the internal energy. The internal energy we can write as the trace of rho density matrix times the Hamiltonian. Rho is a canonical state, so it has the form 1 over a partition function e to the minus beta h, and then we have the Hamiltonian. This is just an explicit way of writing the expectation value of energy. And we can take the 1 over partition function in front and write this as minus 1 over partition function trace e to the minus beta Hamiltonian times Hamiltonian. We can now derive this once more with respect to beta. So we can look at the second order partial derivative of the log of the partition function with respect to beta. And we take the last expression on the previous line as the starting point. So this, we take the first derivative in the form of the last expression on the previous line, and we take once more the derivative with respect to beta. We have a product minus 1 over partition function times the trace. So we, according to the product rule, we first have to take the partial derivative of minus 1 over the partition function, and that is equal to 1 over the partition function squared times the inner derivative, so the partial of z with respect to beta, times the trace. And then we have minus 1 over partition function times the partial derivative of the trace with respect to beta. Now, what's the derivative of an exponential? That's the exponential. So we have e to the minus beta h. And then we get the inner derivative of the exponent with respect to beta, and that is minus the Hamiltonian. So we get minus the Hamiltonian, and then we have still another Hamiltonian in the trace. So what do we have? The 1 over partition function squared, I'd like to separate into two factors. 1 over z, partial z over partial beta. And then here I have my second 1 over partition function, trace e to the minus beta h times Hamiltonian. The second expression, we have two minus signs, they cancel, so in total we have a plus here, and then we have a 1 over partition function, trace e to the minus beta Hamiltonian, and then we have the Hamiltonian squared. What is this? What I just underbraced. This is once more the formula for the expectation value of energy in the canonical state. So this is once more the expectation value of the Hamiltonian. What I have in front, the 1 over partition function dz over d beta, this is once again minus the expectation value of energy. Remember the formula on the first line? This is minus the expectation value of energy. So this is minus expectation value of the Hamiltonian. And the second term in this sum, well, this is 1 over partition function times the exponential. That's the canonical state. So we have trace canonical state times h squared times Hamiltonian squared. So this is the expectation value of the Hamilton operator squared. So this is, in other words, this is expectation value of Hamilton operator squared minus the square of the expectation value. Now the expectation value of h squared minus the square of the expectation value, this is the variance of h. Now the variance is always a non-negative quantity. So what you find that there's a relationship between a second order partial derivative of the log of the partition function and the variance of the Hamilton operator. And this is a measure for the size of the fluctuations of energy. Yeah? So the variance is a measure, or it quantifies the size of the fluctuations of energy. Okay, so we have a formula now for the size of the fluctuations of energy in a system where the energy is not given as a sharp constraint. In that case, you wouldn't have fluctuations because it's given as a sharp value. But if the energy is only given as an expectation value, then of course you can have fluctuations around this expectation value. The size of these fluctuations is characterized by the variance, and the variance in turn can be calculated by taking a second order derivative of the log of the partition function. You can generalize that to the situation where you have relevant observables AI whose expectation values are given. Remember that in this case the macro state had the form 1 over a partition function e to the minus, and then we have a sum over Lagrange parameter times relevant observable AI. According to our general framework, that is the macro state when you are given as macroscopic data the expectation values of arbitrary observables AI that are relevant to your system. Now for this general case, the variance of one of these relevant observables. So again, this is a measure for the size of fluctuations of this particular relevant observable. This is given as the second order partial derivative of the log of the partition function with respect to the associated Lagrange parameter. Now the first order partial derivative with respect to a Lagrange parameter, this gives minus the expectation value. So you can just as well write that as minus the partial derivative of the expectation value of AI with respect to lambda I. And when you take this partial derivative, you keep fixed all the other lambda k's, so k different from I, and in case you have control parameters or other sharp constraints psi, you keep those fixed as well. And a variance is always non-negative, so once again, this is always larger or equal to 0. So this is the general formula for fluctuations of the relevant observables in a macrostate. And what we saw on the previous page was just a special case where you had a single relevant observable, namely the Hamiltonian, and the associated Lagrange parameter was beta. Now these fluctuations that I showed you on the previous page, they are very often related to thermodynamic coefficients. We'll come to these coefficients later. We'll talk about them in a systematic way. But one particular example for thermodynamic coefficient is the so-called specific heat. And for this specific example, I want to show you the relationship between fluctuations and specific heat. More precisely, just in case the system that you consider may be in a container with varying volume, so where the volume is allowed in principle to vary, then you have to specify whether or not you keep the volume constant or you keep the pressure constant. So let's focus on the specific heat at constant volume. The specific heat at constant volume is defined in the following way. It's the derivative of the internal energy of the system with respect to temperature, the partial derivative with respect to temperature at fixed volume, fixed particle number, and you also divide by particle number or number of constituents. In the case of a paramagnet, the example that we discussed, n is the number of elementary magnets. So you keep the number of elementary magnets fixed. In that example, you also don't have volume as a parameter. The only variable that you have is the number of spins. So in that case, it wouldn't be necessary to specify explicitly that you keep the volume fixed. But if you have an ideal gas, so an example that we will come to very soon, in a container, then you specify explicitly that you keep that container at fixed volume. Now, physically, what does that specific heat tell you? It tells you as you increase the temperature of the system, you also increase its energy. You have to supply energy, you have to supply heat in order to increase its temperature. And the amount of energy that you have to supply in order to increase its temperature, that is characterized by the specific heat. Now, in case, as we had in the example of the harmonic oscillator, that you know the energy as a function of inverse temperature beta, you know U as a function of beta, then you can apply the chain rule and you can write this partial of U with respect to T. You can write that as partial of beta with respect to T times the partial of U with respect to beta at fixed volume and number of constituents n. Now beta is equal to 1 over kt, so the partial of beta with respect to t, this is minus 1 over kt squared. And the u in turn, the internal energy, we know this is minus the partial with respect to beta of the log of the partition function. And so we use this formula over and over again. We have a canonical state, then u is given by minus d over d beta of the log of the partition function. So using these two relations, we have two minus signs that cancel. We have a 1 over nkt squared. And then we have, in total, we have a second order partial derivative of the log of the partition function with respect to beta. Again, to make this clear, at fixed volume and particle number. But this, we just learned, is the variance of the energy. So, in fact, the specific heat at constant volume is related to fluctuations. It's related to the variance. It's given by 1 over nkt squared times the variance of energy. And this is, of course, we learned this is always non-negative. So in particular, the specific heat is also always non-negative. So we find that the specific heat is related to the size of energy fluctuations.